Okay, in this video we'll use Faraday's law to show how we can induce an EMF. We can induce an EMF in a closed loop. It says the magnitude of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux is changing with time. So our EMF symbol is actually equal to the negative of the rate that flux changes with time. That's one version of Faraday's law that has to do with the induced EMF. So the induced EMF opposes, that's what our negative sign means. It opposes the change in flux, that's what that negative sign means. That we'll look at with Lenz's law. Right now we'll just look at the rate that flux changes with time. If we have n coils, instead of just one coil, if we have two coils, we have to be 2 times the rate that the flux changes with the time, 10 times. The magnitude of that EMF, then, since our flux is the closed integral of our B dot dA, so our flux, if you recall from the last video, it's the product of our magnetic field times the area of the loop, so where the magnetic field is parallel to the normal vector to the area of the loop. So that's where we can expand our dot products, or our B dA cosine of theta, where theta is that angle difference if we have a closed loop. If we are normal to the vector, to the cross-sectional area, that's our area vector. If our magnetic field is pointing off in this direction, that would be our theta. So if we want to change the EMF in a coil or induce an EMF in the coil, then we can change the rate that the magnetic field is changing with time. We can change the rate that the area of the loop is changing with time. Or we can change the angle between the magnetic field and the flux. So we could rotate the loop. And that's really what our electric generator is, where we're rotating a loop and we're changing that changing the angle between the flux and the area. So let's take a look at this example. We have a graph here that shows how our magnetic field changes over time. It says we have a uniform magnetic field. Uniform means it doesn't change with space, it just changes with time, we see, but not with space, not spatially. And that exists in a conducting loop, and the direction of the field is perpendicular to the plane of the loop. And then, so we want to rank these 5 regions where the rate that our magnetic field changes with time is different in each of these 5 regions. So we can draw a diagram of of a conducting loop showing our magnetic field being perpendicular to the plane of the loop, so it's parallel to the area vector for the loop. So our theory, again, our EMF is the negative of, that's our Lenz's law, the rate that the flux changes with time. And our flux, we show a double integral because an area integral is a 2-dimensional integral. If it's a circle like this, a closed circle loop, then we can do that with just one integral, but it's still a closed integral. So our dflux dt, then, if we expand our version of flux, then we have, that's the rate that this B dot dA, the integral of B dot dA, changes with time. So we can't just say the inverse of the derivative is the integral, since it's the derivative with time, but it's the integral over area. So we expand our cross product. If the magnetic field is uniform, we can pull it out of the integral. It doesn't change with area. And the closed integral of our area is just the area itself. So in this case, the only thing changing with time is magnetic field. So if we rate this magnetic field, the rate the magnetic field changes with time on our graph, that just becomes the slope. So here we have a slope. Here we have a slope that's in fact negative. And here we have a slope that's also negative. Now we're just comparing the magnitude of the EMF. So we'll look at Lenz's law to decide what happens. What's the difference if our magnetic field is increasing with time or decreasing with time? But time period A and in time period C, the magnetic field is not changing with time, so we should have 0 EMF. So we can solve for that, the magnitude of a magnetic field during time period B here is whatever this, if this is B naught, and if each of these time segments is the same, we'll say each of these time segments is some T naught from here to here and from here to here. These are all the same time periods. Then that would be B naught over T naught. If that's 1 times A, our EMF induced in period D and period C, the magnitude of that, well, that slope is just going to be half of, since this is a straight line, then each of these slopes would be half of the slope in time period B. So, and these two would be the same, so these EMFs are equal, and A and C are equal to 0. So there's an example of EMF induced in the loop, how it changes during the time that this 0 EMF and EMF magnitude, B naught over T naught over A, then it goes back to 0, and then it decreases to half the magnitude, and we'll also show with Lenz's law it reverses direction. So let's look at another example. Here we have a coil that's located inside of a solenoid. So this coil has fewer turns. It only has 130 turns, where our solenoid has 220 turns per centimeter. So 130 turns, that would be number of turns, we've used capital N. 220 turns per centimeter, that would be our lowercase n. That's turns per unit length and number of turns. We're given the diameter of the solenoid, we're given the diameter of the coil, and we're given that the current in the solenoid is reduced to 0 from initially a steady rate, it's reduced to 0 at a steady rate over a time of 25 milliseconds. So we want to know what is the magnitude of the EMF induced in this coil while the current in the solenoid is changing. So what we're looking at, if the current in this solenoid, I think it shows an X down here and a dot up here. So if we use our right-hand rule, we know right at the center of this solenoid, it's going to produce a magnetic field in this direction, and it's going to be uniform at the center of the solenoid. We know that magnetic field from a solenoid, well, the magnitude of that will be equal to our mu naught I current through the solenoid times the turns per unit length, which we're given. And we don't know the current, but we know that the current is changing with time. So then, that rate that dB dt is changing with time is our mu di dt. That's our mu naught, permeability constant, and our turns per unit length. So as that changes with time, that's going to induce an EMF in this coil, and we want to know what is the magnitude of that as this current is changing. So we have our problem diagrammed. We can specify all our givens. We'll give a subscript of S for the solenoid, and we'll give it a subscript of C for the coil, and we want to know what is the EMF in the coil, just the magnitude of that. If we know the initial current at time t is equal to 0 was 1.5 amps, it reduces to 0 amps, and it does that in 25 milliseconds. So the di dt, since it decreases, it's negative 60. That's wrong. That should be 60 amps per second, right? So our theory that we should use then, we know we'll use a theory for an EMF, because that's what we're trying to find. So we're trying to find that. We're trying to find it. It's relative to the rate the flux changes with time. We have our theory for our flux, and we have our theory for the magnetic field of the solenoid. We also need the area theory for the area of the solenoid. We're given the diameter of the solenoid, so we can determine actually what we need. This is going to be for the coil, so we're given the diameter of the coil. That's what we're going to need, and then we'll be able to use our givens to be able to solve, and we need to find our d flux dt we talked about in our last page. So our analysis, again, we know that we want to find the EMF in the coil. That's the number of turns in the coil, the rate that the flux changes with time in the coil, and then our flux in the coil is going to be the flux of the solenoid, because that's the magnetic that's sitting at the center of our solenoid. So our flux in our solenoid, our B dot dA, that closed integral. We can expand our dot product, cosine of 0, because our coil is the axis of our coil is parallel to the axis of the solenoid, so we'll have an angle of 0 degrees. Our magnetic field is uniform at the center of the coil, so we just end up with the flux of our solenoid is our magnetic field produced by the solenoid, but the cross-sectional area here of our coil. So our EMF theory, if we expand that theory, the only thing changing with time is magnetic field. So we get area times the rate that the magnetic field changes with time, dB dt. And then we can specify specifically for our coil, our N is the number of turns in the coil, the area of the coil, and since it's at the coil, it's the rate that the solenoid magnetic field that it's producing is changing with time. Then we can plug in and calculate our area for the coil. We can plug in for the magnetic field of our solenoid, mu naught, times the turns per unit length. So it's 220 turns per centimeter. That's 22,000 turns per meter. And use our dIdt, which is also negative. So we have two negatives, so we would end up with a positive EMF, but we're just solving for the magnitude of the EMF anyway. So when we plug in, we end up with 75 millivolts. So this coil will have an EMF induced about it of 75 millivolts. And that negative sign, again, we haven't learned yet what that really means. That's our Lenz's law. Let's look at another example here. We have a rectangular coil. It has N turns. It has an area of B times A, and it's located in a uniform magnetic field, but it's connected to these co-rotating cylinders that, against metal brushes, they slide to make contact. That's the concept of our electric generator. If this can rotate, it will produce a current. What it will also produce is an EMF. So that's how we can use this rotating motion, torque, to create a current. And we want to show that our induced EMF is a function of 2 pi f, the frequency at which it's rotating with time. So the sign of that, and it has an amplitude here of 2 pi f times the number of turns, the area of the coil, and the magnetic field. So we can show that again, our flux, that's our integral of B dot dA, or our BA cosine theta, but theta here is omega t, because theta is changing with time. This is rotating, if you can imagine, it's going to rotate out towards us and around in this direction. So it's going around and around at a rate, of omega radians per second. Radians per second times the time will give us that angle at any specific time. So our cosine theta, cosine omega t. When we go and take the rate that flux is changing with time, the magnetic field and the area of the loop aren't changing with time, just the angle is changing with time. So the derivative of our cosine gives us the sine, and our omega, in fact, is 2 pi f. So we plug in 2 pi f, and we get, we did solve for show that this is in fact the EMF induced. So then there's going to be a current that's going to flow through this resistor. Well, what is that current going to be? Well, we have our theory that V is equal to IR. An EMF has a unit also of voltage, so our EMF is equal to is equal to IR. So our I is going to be equal to our EMF divided by that resistance. The question is, what direction does the current flow? Well, it's changing with time, so it's going to change constantly in direction. So that's it for this video.